Hi everybody, this is the second video on inductors, so watch the other one first, and this is a short one, and this is covering the energy that's stored in an inductor and about time constant. So because the current increases much slower when there is an inductor in a DC circuit, or it falls to zero in a it takes time to fall to zero when an inductor is in a circuit, brings us to what's actually happening within the inductor while it's opposing this change in current. So while the current is increasing, what the inductor does is it has a magnetic field within it. You know, solenoids, coils of wires have in it a magnetic field or flux because of the current in it. Now it's storing energy in this magnetic field, which is actually released when at switch off. Okay, so and the amount of energy that's stored in an inductor is electric potential energy. It's stored in the magnetic field of the inductor, and it's equal to half Li squared. So it depends on the maximum current and the inductance. So that's what the energy stored in the inductor depends on. I just want to point out one main difference between the capacitor and the inductor. They both store electric potential energy. A capacitor stores electrical potential energy in its electric field because there's a potential difference between the plates. An inductor within it has a magnetic field and it stores its energy in its magnetic field. Okay, right. Now the other thing that I'm going to talk to you about is time constant. Now because the current takes time to reach a maximum, okay, or takes time to fall to zero, as well as there's going to be a changing voltage across the inductor. We look at it in a moment. This is all governed by the time constant. It's a time taken for the current or the voltage to change by 63% of its maximum value. And there are many ways to calculate time constant. One is from the graph, the other one is using a formula, and what time constant depends on for an inductor is tau, which is the same symbol as we used for capacitors, is equal to L over R. So it depends on the inductance as well as the resistance. So if the resistance of the circuit is very high, what's going to happen is it's going to take a very short time. Okay, the time constant is going to become very small. It's going to happen really quickly. And if the inductance is very high, if the inductance is very large, then it's going to take much longer for the current or the voltage to change by 63%. And we're going to see how this is used in certain situations. Now, if you have a circuit, a DC circuit, let's say there's a switch, and we have what's called a neon lamp, okay? And then you also have an inductor in this circuit. Just draw a little resistor as well if you like. Okay. So that's an inductor. This is your inductor, L, that's your resistor, and this is a neon lamp. And there's your switch, there's your DC supply. Now the thing with neon lamps is that it takes a very high voltage to ride. So these neon lamps need about 90 volts to actually light up. Okay, and let's say our DC supply here is maybe a 3 volt, 9 volt, let's say it's a 3 volt DC supply. And you think, how on earth is a 3 volt DC supply ever going to give enough energy for a 90 volt neon lamp to light up? Okay, so this is what you do. So when you close the switch, you see that nothing happens. The neon lamp doesn't light, okay? However, when you open the switch, you find that the neon lamp lights up. Why is that happening? So that means when you open the switch, there's a voltage that's close to 90 volts. And when you open the switch, what happens is that this inductor is discharging through here. this circuit is working. When the switch was closed, nothing happened here. The inductor was storing energy in its magnetic field. Now this is how you reason out. When you open the switch, there is over here an air gap. Air has infinite resistance. Okay, now because air has infinite resistance, the current rapidly falls to zero. So what's going to happen to your time constant? The resistance is very, very high. Okay, so because the resistance is very, very high, your time constant is going to become very, very small. So the rate of change of flux is going to be very, very swift. The flux is going to change so rapidly in a very small amount of time, it's going to fall very quickly to zero. Now, because the rate of change of flux is so high, then a huge voltage is induced across the inductor, and that's what powers your neon lamp. Okay, and the other thing you could think about is that when the switch was closed, the voltage across the inductor could never be more than the supply voltage. It couldn't be more than 3 volts. But when because that's obeying Kirchhoff's laws for closed circuits. However, when the switch is open, the Kirchhoff's law is no longer obeyed over here because it's an open circuit. And so the voltages can reach very high values. So that's how. So the basic thing is, the rate of change of flux is so high that very high voltages are induced. So I hope that made sense. Okay, so I might just stop that there, and I'll do another little video about transient current and voltages across the inductor.